Against the backdrop of major global events, the awarding of the Nobel Prize in Physics in 2022 remained in the shadows. Quite unfairly, as the prize was awarded for proving that our universe is not real. Yes, you heard that right. Reality turned out to be more complex than it seems, and Elon Musk's theory that we live in a simulation has taken on new dimensions. In the next couple of minutes, we'll try to explain the revolution in understanding the universe and space in simple terms. Let's start with understanding what is considered real from a physics standpoint. Paradoxically, this question has been a problem for the scientific community for centuries. Intuitively, we can distinguish our dream with Scarlett Johansson riding an otter through Hogwarts from reality. But science dislikes intuition. It loves precise definitions and dry formulations. You've probably often heard definitions like local realism, reality at a local scale, and other variations, where the word reality is combined with locality. This is the very definition of reality that existed before 2022. In physics, something is considered real if it has certain definite characteristics regardless of the observer. Scarlett Johansson exists only in your dream, appearing and disappearing, but a New Year's mandarin in the store will still be orange before you go shopping. There's a popular philosophical question about a tree falling in a deserted forest. Will there be a sound if no one is there to hear it? From a physics perspective, the question has long been irrelevant. Of course, there will be a sound. The tree has physical characteristics, and therefore its interactions with the surrounding world will not always be predictable, but always according to the laws of physics. And people in this equation are just eardrums to catch the sound. In other words, knowing the characteristics of an object, its behavior can always be predicted. This is essentially Newton's second postulate of reality. The famous scientists argue that if you know the positions, velocities, and characteristics of objects, as well as all the forces acting on them, you can easily predict what will happen to them in the future. And also in the past looks ironclad, doesn't it? Even Einstein supported Newton on this. In all astronomy, what's there? Planets, asteroids, and other galaxies are discovered precisely following this principle. Now we know the characteristics of the sun, its speed, and all the forces acting on it, and we can easily predict that the next solar eclipse will occur in 2024. By the same logic, Uranus is discovered, and the fate of objects in the solar system is mapped out for millennia. The word local is added to the definition of reality to clarify the process of interaction between objects. Only objects nearby can influence each other, and the speed of propagation of this influence has a familiar limit in the form of the speed of light. It's important to understand that in physics, local and nearby objects don't necessarily mean physically close. The star Aldebaran, 65 light-years away, is considered local for an observer on the light from it falling on the human eye's retina and interacting with it is local because it spreads through nearby space and doesn't violate any laws, spreading, forgive the pun, at the speed of light, but not faster. In other words, locality is a caveat to exclude esotericism, the supernatural, and other conventions from the definition of reality. In general, the definition of reality is solid and logical, and then quantum mechanics came onto the scene. You're probably familiar with the experiment with electrons and two slits. If you don't observe the electrons, they behave like waves. If you add an observer, the electrons get disturbed and start behaving like particles. The description, of course, is very superficial, and we apologize to all physicists in advance. We don't need to delve into the experiment itself right now, but the main thing to understand is that quantum mechanics has been breaking the classical definition of reality since its inception. The mandarin on the shelf in the store is always orange even if nobody is looking at it. So an electron, theoretically, should be a perfectly defined object from a physics standpoint and behave the same regardless of whether someone is looking at it or not. But reality got a crack, but in the early 20th century, few paid serious attention to it. Einstein, for example, didn't consider the two-slit experiment and similar ones to be fake until his death. The scientists believed that we simply didn't have the necessary instruments, accuracies, and laws by which these particles behave. In his understanding, the definition of reality didn't falter. It's just that the level of physics couldn't yet grasp the behavior of the tiniest particles. That's where the XX century went, under the auspices of the rivalry between two systems. On one side were quantum physicists who with each passing year discovered increasingly mystical and enigmatic properties of elementary particles, claiming that our world operates completely differently. On the other side were classical physicists who condescendingly stated that someday we'll tie it all together. We just lack the strength now. The battleground of these two systems became the Einstein-Podolsky-Rosen paradox, or simply EPR. When studying the behavior of elementary particles, quantum physicists horrifyingly realized that they could exist in two places at once, possess two characteristics simultaneously and influence each other. The electron, which we remember from school physics lessons as a sort of satellite orbiting an atom, turned out to be completely different. In reality, the electron is simultaneously present at every point of its orbit, just with different probabilities. You're probably somewhat familiar with Schrödinger's equation and other quirks of quantum systems. However, the EPR paradox stands out, if nothing else because it's scientifically proven that it's impossible to explain it from the perspective of ordinary physics. To understand the paradox, imagine that you and your friend Vasily have gone to different ends of the solar system. From Earth, two coins are tossed to you. They start spinning, and at the moment when Vasily sees whether his coin landed heads or tails, he'll know exactly which side your coin landed on. Sounds silly, because it's purely random, and Vasily shouldn't know what will happen to your coin based on his data. However, in the quantum world, everything is just like that. Moreover, in the experiment, Vasily not only learns about the state of your coin, he directly influences it. Einstein famously said about this, "God does not play dice." However, modern research shows that indeed he does. Quantum teleportation was described in 1993, and in a nutshell, it involves creating a pair of coins similar to our experiment. They are quantumly entangled, and as a result, at a great distance, we get a coin whose state is predictable depending on the first coin. And it doesn't matter how far away it is. It sounds like magic, but in June 2017, Chinese scientists teleported a particle over a distance of 1,200 kilometers using the MOSI satellite. This, of course, isn't exactly teleportation. The procedure is more akin to cloning the state of a particle and reproducing it elsewhere. But however you twist it, it works, and there are dozens of successful experiments. Which brings us back to the question of the reality of our world. It's logical to assume that by changing its state during quantum teleportation, particles somehow exchange information. The snag is only that in this case, it happens faster than the speed of light, which is impossible in the current definition of local reality. At the very least, the expression of locality is under attack due to the violation of the speed limit. It got even worse when the postulate that elementary particles have a predetermined state came into question. This is precisely the subject of the work of John Clauser, Elaine Aspect, and Anton Zeilinger, the Nobel Prize laureates of 2022. They studied photons and other elementary particles, trying to find an answer to Einstein's question: do we lack the equipment to measure the characteristics of tiny particles, or do they not exist until we measure them? The team of scientists proved that elementary particles have no characteristics. They only appear at the moment of measurement, and therefore, our universe cannot be called real. To understand this vividly, let's return to the two-slit experiment. Yes, the behavior of particles and the pattern they form depend on the observer, but we cannot predict where exactly a specific particle will land. Einstein believed that we lacked the knowledge to predict its behavior, but the Nobel laureates proved otherwise. Some aspects of the quantum world are indeed unpredictable and random. Tiny particles have no physical parameters until we measure them, and there are no laws, formulas, or definitions that we lack to connect quantum physics with the ordinary. It needs to be studied as it is. For our reality, friends, this is a quiet horror. It turns out that the universe behaves differently at different scales, and it's impossible to pack it into human logic. What's predictable in our visible world is unpredictable in the quantum world. However, ultimately, all objects in the visible world are still made up of quantum particles, which are absolutely unpredictable and only show their characteristics when observed. And funnily enough, somehow the connection between two absolutely different worlds works. Such is the conundrum. The most excited about the Nobel Prize in physics are Elon Musk and other prominent supporters of the theory, stating that our world is a simulation. Indeed, simulation in the quantum world closely resembles the principle of operation of modern machine learning neural networks. They don't have a picture of a raccoon in a RoboCop suit on their hard drive, but if asked, the neural network will generate a result. So too, tiny particles have no characteristics until an appropriate request is made to them. Are we in someone's computer that saves resources and doesn't bother with rendering fine textures until we look at them? Unfortunately, it's hard to deny. However, underestimating the epochal nature of these physical discoveries is also ill-advised.